Let us take another example. Let us say there is a wheel which is thrown this way with a velocity v, and it is moving on a smooth surface. There is no friction here. Suddenly it encounters a rough surface. The surface is so rough that it starts rolling right away. So here it was just moving, there was no rotation, there is no rotation of the wheel about the center of mass, and as soon as it hit this rough place, it started rolling, so that its lowest point was stationary at that point. What about its rolling speed? So let us see what has happened. The moment it hits this rough patch, it gets an impulse j in this direction. Initially, if it was moving with momentum v, this momentum now gets reduced because of this impulse. So that comes from momentum equation. Not only that, if it is rolling, then it should also be rotating about the center of mass with the speed v1 over r, and therefore it has gained an angular momentum about the center of mass. Where does this angular momentum come from? That angular momentum comes from the impulse that it got here. So the torque impulse it got is equal to j times r with respect to center of mass. So the angular momentum it should obtain about the center of mass should be equal to j times r, and this tells you I is m r square, omega is equal to j times r, r cancels, r times omega is v1, so m v1 equals j, and therefore putting this in this equation I get mv minus m v1 equals m v1, or v1 equals v over 2. So as soon as this wheel which is moving with speed v without rolling on a smooth surface hits a rough surface here, it will start rolling with speed v over 2. As a third example, let me take a rod, and you must have seen this if you sometimes drop things. Let its initial angle from the horizontal be phi, and let its height from the ground be h, and let it drop. You must have seen it happen at home. If you drop something like this, it goes back and forth and you hear a voice tuck 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 tuck. So what I want to know is, after it hits the floor and suppose no energy is lost, what will be its rebound velocity and what will be its rebound omega. When it drops from a height h, when it reaches here, its velocity is going to be the square root of 2 gh. So, and when it hits here, there is an impulse that acts here, let that be called j. So I am going to have square root of 2 gh times the mass of the rod minus mv, this is the loss in the momentum, that should be due to j. That is from momentum equation. Similarly, now I apply the torque equation about the center of mass, which is again the safest point to apply it from. This j gives you a torque impulse. This distance is going to be L over 2 cosine of phi if the length of the rod is L, and therefore torque impulse is going to be j L divided by 2 cosine of phi, and this must give it an angular momentum about the center of mass I omega, or m L square over 12 omega is equal to j L over 2 cosine of phi. That's equation number 2. I have 3 unknowns, V, omega and J. So I need one more equation, and that comes from energy conservation. The energy conservation tells me that the energy that it gained while being dropped, the kinetic energy it gained, is going to be equal to mgh, and that should be equal to its energy right after rebound, and that is going to be 1/2 mv square plus 1/2 I omega square, which is equal to 1/2 mv square plus 1/2 ml square over 12 omega square. M cancels, and therefore you get 2 gh equals v square plus L square omega square over 12. So now I have got 3 equations to solve to get my answers. The 3 equations are m is square root of 2 gh minus mv equals j. Then I have ml square over 12 omega equals j L over 2 cosine of phi, and third equation I have is 2 gh is equal to v square plus L square over 12 omega square. Substituting things properly, I can get my answers from this, and this I leave as an exercise for you to solve. As the last example I take is a very interesting one and a very famous one. It is, if I have a ladder leaning against a wall and on the floor here, and suppose there is no friction, then the ladder obviously would start slipping like this. The question is, if initially it was at height h, at what height does the upper end of the ladder leave the wall? If I make a free body diagram for the ladder, there is going to be a reaction N1 here and N2 here. The point at which N2 vanishes is going to be the point where the upper end has left the wall. So what we want to determine is N2 and make it 0 to find this out. Let us see what is happening as the ladder comes down. As the ladder comes down, its center of mass has moved down. Not only that, the ladder has rotated about the center of mass. So it has both a translational as well as a rotational motion. However, all I need to describe its complete motion is this angle it makes with the floor, because the center of mass of the ladder is going to be given by this itself. So let us make this picture again. Here is the ladder of length L. If this angle is theta, center of mass is right here, you can see that x cm is going to be L over 2. This is x cm, L over 2 cosine of theta, and y of center of mass is going to be L over 2 sine of theta. So for this ladder, I have x cm is equal to L over 2 cosine of theta, and y cm is equal to L over 2 sine of theta. This is N1, this is N2. How about equations of motion? The mass of the ladder times x cm double dot is obviously going to be N2. This is x direction, this is y direction. Mass of the ladder y cm double dot is going to be equal to N1 minus mg. That is for the translational of this center of mass, equation 1, equation 2. On the other hand, it also rotates as it moves, and it is rotating like this. For the rotational motion, n1, n2, since we are taking theta like this, we will write the equation that way. I am going to have I theta double dot about the center of mass is going to be equal to n2 times this distance, which is L over 2 sine theta, minus n1 L over 2 cosine of theta. This is my equation number 3. So, I have 3 equations, but unknowns seem to be more: xcm, ycm, theta, n1 and n2. However, xcm and ycm are not independent, because as we saw, xcm is equal to L over 2 cosine of theta and ycm is equal to L over 2 sine of theta. Let us now write expressions for n1 and n2. X cm is equal to L over 2 cosine of theta, and therefore xcm dot is equal to minus L over 2 sine theta theta dot, and therefore xcm double dot is equal to minus L over 2 sine theta theta double dot minus L over 2 cosine theta theta dot square. Similarly, let us derive y cm double dot. Y cm is equal to L over 2 sine theta, and therefore y cm dot is equal to L over 2 cosine of theta theta dot, and y cm double dot is equal to L over 2 cosine of theta theta double dot minus L over 2 sine theta theta dot square. And therefore, we can write expressions for n1 and n2. n2 would be equal to m times x cm double dot, which is m minus L over 2 sine theta theta double dot minus L over 2 cosine theta theta dot square, and n1 would be equal to mg plus mycm double dot, which gives me mg plus m L over 2 cosine theta theta double dot minus L over 2 sine theta theta dot square. So, these are equations that give me n1 and n2. Similarly, I theta double dot is equal to n2 L over 2 sine theta minus n1 L over 2 cosine theta, as we wrote earlier. Let us check that. I theta double dot is n2 L over 2 sine theta minus n1 L over 2 cosine theta. Now, if I substitute for n1 and n2 here, let us see what do we get. We get I theta double dot is equal to L over 2 sine theta, n2 is minus m L over 2 sine theta theta double dot minus m L over 2 cosine theta theta dot square plus mg plus ml over 2 cosine theta theta double dot minus ml over 2 sin theta theta dot square times minus L over 2 cosine of theta. Let us see what do we get when we add these two. So, on the left hand side I get ml square over 12 theta double dot is equal to minus mgl over 2 cosine of theta, that takes care of this term. Then I am going to have minus ml square by 4 cosine square theta coming from here minus ml square by 4 sine square theta coming from here, that will give me minus m L square over 4 theta double dot, that takes care of this term and this term, and finally I am going to have plus ml square by 4 sin theta cosine theta theta dot square from here and plus ml square by 4 sin theta cosine theta theta dot square from here. So, that term cancels. So, this is my final equation. When I substitute for N1 and N2 into the equation for torque, if I take this over to the other side, I am going to get m L square over 12 plus m L square over 4 theta double dot is equal to minus m g L over 2 cosine of theta. This is m L square over 3 theta double dot is equal to minus m g L over 2 cosine of theta. I want to integrate this equation, and therefore I am going to write theta double dot as equal to d over d theta of theta dot square over 2, and therefore this equation becomes 1/2 m L square over 3 d over d theta theta dot square is equal to minus m g L over 2 cosine of theta, and that this 2 cancels, and that gives me m L square over 3 theta dot square is equal to minus m g L cosine theta d theta is starting from the initial angle theta 0 to some angle theta, and that is m g L sine theta 0 minus sine theta. This is the final equation that I get. A note here, this is really nothing but the energy conservation equation. I would leave it for you to find out that the change in PE of the ladder is equal to the KE of the ladder, which is equal to KE of Cm plus KE about Cm would directly lead you to this equation, but I wanted to derive this equation using equations of motion. Nonetheless, this equation is now the equation that would lead to the answer. So, please try this, that derive this directly from the energy conservation equation. This divided by 2 would give you the change in the potential energy, and these two terms together would give you this term. So, I have m L square over 3 theta dot square is equal to m g L sine theta 0 minus sine theta. So, I get the value of theta dot square. Similarly, I already have mg, the value for theta double dot, and if I substitute these in the value for N2, I will get an expression for N2. Let us go to the expression for N2. N2 was equal to minus ml over 2 sin theta, theta double dot minus ml over 2 cosine theta, theta dot square. And let us substitute. Let us cancel this, let us cancel m, and this gives me theta dot square is equal to 3g over L sin theta 0 minus sin theta. Similarly, the equation for theta double dot, which we had derived earlier, this one, ml square over 3 theta double dot equals minus mg L over 2 cosine theta. Let us write that ml square over 3 theta double dot is equal to minus mg L over 2 cos theta, gives me m cancels, gives me theta double dot is equal to minus 3 divided by 2 g over L cosine of theta. Substituting these in the expression for N2 here, we get N2 is equal to minus ml over 2 sin theta minus 3 over 2 g over L cosine of theta, and the next term is minus ml over 2 cosine of theta, and for theta dot square I get 3g over L sin theta 0 minus sin theta. So, this gives me minus 3, this L cancels, 3 over minus minus plus 3 over 4 m g cos theta sin theta minus this L also cancels, 3 over 2 mg cos theta sin theta 0 minus minus plus 3 over 2 mg cos theta sin theta. Let us add all of them together and we get N2 is equal to minus 3 over 2 mg cosine theta sin theta 0 plus 3 over 4 plus 3 over 2 is 9/4 mg cosine theta sin theta, and the point where the ladder leaves the wall N2 is 0, and this gives me 3 over 2 sin theta 0 is equal to 9 over 4 sin theta or sin theta equals 2/3 sin theta 0. So, if we start with an angle theta 0 at sin theta equals 2/3 sin theta 0, the ladder would leave the wall. So, let us see the picture again. This is theta 0 at 2/3 of sin theta 0, that means at the height 2/3 of the original height, the wall and ladder would separate. So, sin theta equals 2/3 sin theta 0, or L sin theta is equal to 2/3 L sin theta 0. L sin theta 0 is the initial height, this is the height at which the ladder leaves the wall. So, H equals at 2/3 the original height the wall leaves, wall and ladder separate. So, this is another example of how the combination of translational and rotational motion can be solved. So, what we have done in this lecture so far is considered various applications of the equation dl over dt equals tau external, in those problems where the axis of rotation remains fixed or it translates parallel to itself, in that case we saw that we apply d LO over dt is equal to tau external, where O is either the CM or a uniformly moving point or accelerating towards CM. The safest point to take always is CM, because that you are sure of. And with these we solved certain interesting problems. You can keep making problems more complicated, but the application remains basically of these equations. What I would urge you now is apply these to as many difficult problems as you can. Good reference books to find such problems are Merriam Dynamics and Kleppner-Kolenkov Introduction to Mechanics.